Yes, Muniba, Jesleen, am I audible to both of you? Yes, Muniba, Jesleen.
Yes,
Yes,
ma'am.
ma'am.
Okay. In the last class, we stopped at this point. We were seeing cause of magnetism in matter. First point, I told you that matter at the atomic level, this has the orbital motions which are contributing towards the magnetic field, and the entire orbit of the electron behaves as a magnetic dipole. Just tell me one thing. I think, Jesslyn, you were present. Could you write all these points?
Yes, ma'am.
Okay, then. So we have to start from the fourth one. See, fourth point basically says that some elements are there when we say, no, when I discuss the third point with you, that we say the net magnetic moment is the magnetic moment which we refer for an atom. So for the fourth point, see, some of the magnetic moments get cancelled. They make pair and they get cancelled. Like if you talk about helium, you write it as 1s square. This is how we write it in chemistry. Magnetic moment, basically all the electrons get cancelled. So such materials are known as diamagnetic, which have paired electrons. Because electrons are in pairs, what happens? This electron, they make a pair and their net magnetic moment is cancelled. Similarly, one more electron, they'll make a pair, their magnetic moment is cancelled. So magnetic moments get cancelled, so that materials are called as diamagnetic sections. Whereas sometimes if electrons, what happens if electrons are unpaired? Means electrons are present, but they are not in such a number that the pair can be formed. So magnetic moments do not cancel, and some magnetic moment is still left in the material. Those materials are paramagnetic and ferromagnetic. So we'll discuss about these three again, but just a little bit about the matter concept, the diamagnetic, paramagnetic, and ferromagnetic. You should know from the pair. I was referring to this point that we have the net magnetic moment. We say if an atom is there, its net magnetic moment is empty due to all the electrons that are present. So if the net magnetic moment is zero, we say it's a diamagnetic substance. If it is non-zero, we say paramagnetic and ferromagnetic. These 2 points are clear?
Yes, ma'am.
Yes,
Okay.
ma'am.
Now see, just a little more detail. This is present in your NCRT. If you take a specimen of a matter, so all of these arrows are representing the magnetic moments. It happens that the net magnetic moment, how is it zero? See, if this is, let's say, pointing downwards, other one will be pointing upwards, one will be pointing towards the right, other one will be pointing towards the left. Like this, if one is diagonally up, other one will be diagonally down. Like this, all the magnetic moment will be cancelled. But when I'm referring to one magnetic moment, this one magnetic moment. So in 1 millimeter cube, there are almost 10 to the power 20 atoms. So 10 to the power atomic dipoles will be formed in just 1 millimeter cube. Okay, so this is at a very such micro level. Okay, we are talking about the matter. So when it says a specimen of matter, this is what it is referring to as the specimen of matter. Now, here the net magnetic moment is zero because all of these are now which all of these magnetic moments are getting cancelled, but here there is no electric field present. Electric field is not present. There's just a matter that has been taken. Let's say there's a this is a matter that has been taken, and it has various kinds of dipoles, magnetic dipoles present. Okay, one dipole will cancel the other dipole, this dipole will cancel this dipole, this dipole will cancel this dipole. Like this, all the dipoles will be present. Okay, now, if I apply electric field, so what will happen? All these will have a tendency to get aligned in one direction. All of these will have the tendency to get aligned. Okay, on applying external electric field when you apply. Okay, so when you apply the external magnetic field, due to the magnetic field, what will happen? All of these are see aligned. Aligned means they are in the one. All of these are in one direction. Now, what's the difference? Here they were in the random direction. So randomness led to the net magnetic moment we see. Right? One is pointing 30-degree here, another is pointing 30-degree here. So this way they get cancelled. One up, one down, they get cancelled. One right, one left, they get cancelled. Like this, you have all of them getting cancelled. But if they are aligned in one direction, they won't be getting cancelled. All the vectors pointing in one direction, you will add all of these. So you'll never get net magnetic moment zero if the magnetic field is applied in a matter. Okay, so these were some points. Cause of magnetism from this chapter. Basics of magnetism, if we talk about at the matter level. One was very important, that was the orbital's motion, which we studied, that when the electrons move, it contributes to current, and this current loop acts as a magnetic dipole. So major contributing factor was our orbital motion of electron as well as the spinning of electrons. And magnetic moment due to the nucleus was very small, so I asked you to neglect it. Then when we say the net magnetic moment of electrons of an atom, this is due to all the electrons that are present. So if some electrons they get cancelled and there is no extra electron left, then we say this is a diamagnetic substance. If some electron is still left, we say it's a paramagnetic or ferromagnetic substance. And if we take a small specimen of matter, 1 millimeter cube of material we'll take, and even this small 1 millimeter material cube, 10 to the power 20 atoms will be present. And all these without the magnetic field. Here the magnetic field is zero. So when magnetic field is zero, all of these are in random directions, cancelling each other. Net magnetic moment zero, because all of these are vectors. Two vectors cancelling each other like this. But when you apply the external magnetic field, all of these align in one direction and they give net magnetic moment. So that's why you have magnetic moment in your system when magnetic field is present. If magnetic field is zero, we say magnetic moment is also zero. Tell me, is it clear till here?
Yes, ma'am.
Okay. Please continue from the fourth point. Is it done, class? The writing part?
No, ma'am.
Done?
Done, ma'am.
Okay. See, class, there's a quantity magnetization vector, which in NCRT is represented as capital N. You can use I also. And it has one more name, which can also be given intensity of magnetization. Now, class, two terms are going to come, and these two terms are going to be very confusing. So just pay a little attention. Intensity of magnetization is what? It's basically, I'll use I only, then it will be confusing. Intensity of magnetization is basically magnetic moment per unit volume. That's it. Okay, this is very easy, small terms are now left. Let's complete this chapter. M is what? This is the magnetic moment, while V is the volume. Okay, and this is the intensity of magnetization. So very easy, magnetic moment per unit volume. Magnetic moment is already current into area, so you just divide it by volume. Let's look at one question. It came in one of your exams. It says for a bar magnet with pole strength M and length 2L. Now length, I hope you understand when I say the length of a magnet. Let's say this. Now, if I have the length of the magnet, this will be length is 2L. If I have the north pole here, the south pole here, total length will be 2L. And the magnetic charge is given as M. Cross-sectional area is given as A. It says calculate the value of the magnetization vector. Magnetization vector means intensity of magnetization. That is magnetic moment per unit volume. Okay. Now, when we talk about the magnetic moment, like your electric dipole, we have electric dipole moment, charge into length. This will be the magnetic moment into the magnetic charge into the length separation. So what's our magnetic moment? Magnetic moment is equal to M into 2L. Now volume is what? Volume is also area multiplied to the thickness or length. That's the formula of volume anywhere. So this is equal to area is A, length is L. Now, see, main equation is this. One of the values you have got is this, and one of the values is this. So we combine, we put 2 and 3 in 1. Put 2 and 3 in 1. So we get intensity of magnetization will be M2L by A, L. LL gets cancelled. So this is equal to 2M by A. This was once asked in the exam. Now SI unit. I didn't write the SI unit. See, for magnetic moment, it is ampere meter square, and volume it's meter cube. So it becomes ampere per meter. Okay. Here also we'll have the unit as ampere per meter. Tell me, is this question clear? This topic, this question, anything? Did you get it?
Yes, ma'am.
All right. Write it. Then one more topic which is very similar to this magnetic intensity I'll discuss. But first, copy down this.
Ma'am, I have a
Yes, Maniba, what are you saying?
for the volume, we did area into length, right? But the length is 2L, right?
Oh, yes, yes, you're correct. Area into 2L. Length is given as 2L. So here a 2 will come, so 2 will also be cancelled. We won't have any 2 now. Yes, ma'am, correct. Done?
Yes, ma'am.
Okay. See, now a very similar term is there, magnetic intensity. One we did was intensity of magnetization. Now this is magnetic intensity. It is represented as capital H, and both of these are different. So magnetic field intensity, magnetic intensity, these are represented by capital H. Magnetic intensity of magnetization, or this magnetization vector, these two terms, magnetization vector or intensity of magnetization, this is different. But the names are so similar that it can be very confusing at times, because magnetic intensity is intensity of magnetization. It looks like this, but it isn't. The intensity of magnetization means how much magnetic moment is there in 1 meter cube. Means this that we discussed, no? In 1 meter cube, how many atoms are present in 1 meter cube? What is the magnetic moment existing? This is what is meant by intensity of magnetization. How intense or what's the strength of the magnetization is in 1 millimeter cube. See, when we talk about the magnetic fields inside a matter, it is caused due to two factors. You have a group of internal factors. you have a group of external factors. Okay. When I talk about the internal factors, it's due to the alignment of the dipoles. Some magnetization occurs. Why? Because see, if the dipoles cancel each other, there is no net magnetization, right? Net magnetic moment is zero, so no magnetic field. But in some cases, we saw that yes, magnetization is left. So when we talk about the net magnetic field inside the matter, it is caused because of these two reasons. First is the internal factor reason, second is the external factor reason. So these alignments of dipole which we studied earlier was the internal factor. But if I talk about external factors, if I have a proper device, if I have a current carrying wire, or if I have a current carrying coil, so these are the external factors that lead to magnetism, like a solenoid. So if you have these factors, these are what we call as the magnetic field due to these external factors is what we call as the magnetic intensity, magnetic field intensity. Okay, and intensity of magnetization is what due to these internal factors, magnetic moment per unit volume. Okay, so magnetic field, whenever you have within a matter, it is caused due to two reasons: internal factors, external factors. Internal factors means how these dipoles are arranged within themselves so as to get a magnetic field or not, sorry, magnetization or not. If you're getting some magnetization, that is the intensity of magnetization. But when we are talking about the external factors, like a wire is there which is carrying current, which is producing the magnetic field. Solenoid is there. We know B is equal to mu naught, this mu naught Ni. Formula of magnetic field is B is equal to mu naught Ni. Means this much of magnetic field will be contributed. So all these magnetic fields, these are known as the intensity, the magnetic field intensity. So we can basically say that the net magnetic field that we have, this is due to the internal factors plus the external factors. This is important because see, when magnetic field, and what kind of magnetic field is this? This is the magnetic field which is existing at the matter level. Okay, this is existing at the matter level. The net magnetic field is sum of internal as well as external. So I can say the net magnetic field is directly proportional to H as well as I. So before we go into this, still here is it clear? This internal, external, H and I part to both of you, Jasleen, Muniba.
Yes, ma'am.
Jasleen, what about you?
Yes,
You
ma'am.
getting it? Okay.
Yes,
Now
ma'am.
see, replace the internal part with I, replace the external part with H. So what we'll get here, the constant that comes is the permeability, which you already know. This is the same permeability. This value, this is mu naught, which is the permeability of free space. Okay, this is the same permeability of free space that we write, which is 4 pi into 10 to the power minus 7. So this constant comes here. Okay, now if I have this constant term here, let's say the net magnetic field is there. This is mu naught. Let's multiply mu naught H plus mu naught I. If I open up the brackets, I have to multiply it within the brackets to this as well as to this. So mu naught into H will be mu naught H plus mu naught I into I will be mu naught I. So here, okay, one thing we can do is if I divide this by mu naught, this by mu naught, this by mu naught, this by mu naught, means divide by mu naught. If we divide the equation by mu naught, so we get, what do we get? B by mu naught is equal to H plus I is what we'll get. So from here, the formula of H, the magnetic field intensity will be B by mu naught minus I. Okay, so this is one relation that can be used. Now you have to be very careful with this. Why? What is I? See, from I, it's easy to remember. Intensity starts with I. So remember, intensity of magnetization is this, I. Magnetization. Okay. And the other one is magnetic intensity. So that is it. This is just magnetic intensity. Magnetic field intensity, magnetic intensity. So this is how both of these are connected, and one question came in your board exam for 2 marks in 2015's paper to prove to find a relationship between the intensity of magnetization and magnetic field intensity. So these few, this part, this much calculation you should just be able to perform. Okay, and see, B by mu naught is equal to H plus I. Now, what is mu R? Mu R is, can anyone tell me what is mu R? What is this mu R? No, we did is mu divided by mu. This is for any medium. This is for free space or air, which we say. When you divide them, what do you get? What is this mu R? R stands for what? Yes, Jesleen, Muniba, answer. What is this? Mu divided by mu naught is what? We've done it in Biot-Savart law as well. This is relative permeability. Relative permeability. At least this you should be able to answer permeability. So mu's value will be equal to mu r into mu naught. Now see, B naught is equal to mu naught H plus mu naught I. Remember one condition. In vacuum, the value of I is equal to 0. So you get B naught is equal to mu naught H. Okay. B naught is equal to mu naught H. Now, intensity, when you're talking about the intensity of magnetization, there's a relationship which comes. This is known, this symbol, this is known as chi, okay, which is known as the susceptibility. Okay, I'll come to the susceptibility part later. Do one thing, copy it till here, then it will be a lot. Till here, you copy it till here. Okay, this part, this whole chi part, I'll discuss with you, susceptibility part and all. Small portion is left. See, what have I done? Magnetic field is a sum of internal and external field. So external field will give rise to your H. Internal will give rise to I. So from here we can say B is equal to mu naught H plus I. So that can be written as B by mu naught by mu naught H plus mu naught by mu naught I, which is B by mu naught H plus I. Directly also you can write, but it's just that here no, the proportionality sign is still there. That's why we didn't write it. You can directly write it as well, and mu is equal to mu r into mu naught. So B naught is equal to mu naught plus mu naught I. In vacuum, I is equal to 0. This part I'll discuss. You write it from here. Okay, magnetic intensity.
Ma'am, can you scroll up?
Now done. Till here, this part, rest of it, Maniba, I'll tell you. Then you can write it. Okay, this much part. Is it done?
Yes, ma'am.
See, the susceptibility, let me tell you what exactly susceptibility. Susceptibility means this symbol. This is used to represent susceptibility. Susceptibility means how easily a material can be magnetized. If susceptibility is more, then we say the ability of the material to get magnetized is more. Okay, so I is equal to susceptibility into H. This is the relation. Chi, we call this symbol is known as chi. So I is equal to chi into H. When you have Bm is magnetic field for any medium, Bm is equal to mu naught H plus I can be written as chi plus H. Okay, so from here if you take H common, so mu naught H 1 plus the susceptibility will be left. From here if I take mu H common, Now see, mu naught 1 plus susceptibility is basically one more formula you have. The permeability of any medium is equal to the permeability of air 1 plus the susceptibility. These are already derived formula. You don't have to derive these ones. You just have to remember their meanings. So this way you get the relationship between magnetic field, permeability, and H for a medium, and this is for air. Already this was matching from here itself. B naught is equal to mu naught H. So for a medium, it will be Bm is equal to mu m into H. Otherwise, this way also you can go. But the susceptibility is important, how easily a material can be magnetized. This hasn't been written anywhere, no? I'll just write it here. Okay, at the end, I'll just add it. So mu m is equal to mu naught 1 plus susceptibility. Now, if I have the relative permeability, see, from here, what will be the value of mu naught? Look. Yes, Muniba, you tell me what will be the value of mu naught from this formula? Yeah, Muniba, what is mu naught from this formula?
4 into 10 raised to minus 7.
No. Means if I want to write it in terms of B and H, how should I write?
Mu naught is equals to B naught by H.
B naught by H. Very good. And Jaslene, could you tell me for the permeability of any medium from here? How should we write it? Yeah, Jaslene. Bm by H. Yes, this is equal to Bm by H. So see, if I take the relative permeability, I'll have to take their ratios. Mu naught divided by mu m is the relative permeability. So from here, if you put Bm by H into B naught by H, H will be cancelled. This is an important factor because this this gives you a comparison about the magnetic field of a medium and the magnetic field of air. Okay, so how by which factor is the magnetic field increasing? See, this is giving you the factor by which the magnetic field increases on introducing into some materials. Mu m is equal to mu naught 1 plus this. So let me just mention a little about this. What is susceptibility? Susceptibility is how easily materials can be magnetized. Okay, that's all. Now, one numerical. Let's come to the numerical. See, it says a solenoid has a material of relative permeability 400. So, relative permeability is given, means you have mu r given as 400. Then it says if solenoid has 1000 turns per meter. Is this capital N or small n? 1000 turns per meter. This one. Is it capital N or small? Per meter, per unit length. Small n. Okay. So this is 1000 turns per meter. So this is small n. And carries a current of 2 ampere. I is equal to 2 ampere. This is given to us. Now it says to calculate the value of H, to calculate the value of the net magnetic field and I. Now see, here we did a relationship. Bm is equal to mu m into H. Okay, we have the relative permeability with us. Yes. See, when you have the relative permeability, you know mu naught. Mu naught is already 4 pi into 10 to the power minus 7. Yes. The relative permeability, this mu naught is equal to 4 pi into 10 to the power minus 7. Already you have it. Okay. Now, for the magnetic field, we have the formula mu naught n I. This is the formula of the magnetic field. If whenever you have a solenoid, here a solenoid was given, so this is our formula. Now it says to calculate the value of H, the net magnetic field, and to calculate the value of I. So if I have mu r, mu naught, and this is the magnetic field due to air only, this will give me B naught. So using B naught, I'll be able to calculate the rest of the value. See what will be B naught equal to. 4 pi into 10 to the power minus 7 into this is 1000 into 2. So how much it will be? This will be 8 pi into this will be 3 10 to the power minus 4 Tesla. This is what? This is your B naught. Okay. Now see, B naught will only give you this. What do we have? B naught and mu naught you have. Now H can be calculated if I take the ratio of B naught and mu naught. So for the first part, I'll have the B naught was missing. So B naught is equal to mu naught into H. So what will be the value of H? H will be B naught divided by mu naught. B naught is 8 pi into 10 to the power minus 4. This is 4 pi into 10 to the power minus 7. So zeros will come. 2 into, see this becomes 3, 2000. Okay. And see for the, yes, unit we didn't discuss of H. No, we haven't discussed the unit of H. See, intensity of manipulation, basically you just have to understand that the unit is exactly the same as that of I only. Okay, so here also you will get ampere per meter square. So I'll just directly write it here. You just add that point, ampere per meter square. Then you have the second part says net magnetic field. Now net magnetic field is mu naught. You can use H plus I, okay, for the net magnetic field. So for that purpose, we'll require I, okay, the value of I. Now look, this part you haven't written, no? I'll give you space to write. So B naught we have got, mu naught we have got, H we have. So from here we'll be able to calculate the value of I. Okay. Now one more thing, class. When you are calculating this BM is equal to mu H multiplied to mu M into H. So this formula you can use. BM is equal to mu naught H plus I. Okay, BM is equal to mu naught H plus I when BM is there. Now, how do you know BM is given? Because you have the value of mu R and mu naught. So you can calculate the value of mu M. So, but that's a very lengthy method. You shouldn't prefer that. Okay. So B net and I, let's calculate, or do one thing. Just write it till here first, then I'll complete this question. Because I have to scroll it so that you are able to see. Other than once you will write it, you just can turn the pages of your notebook. Okay. So just write it. Then it will be easier to solve the question. First write down this part. Till here you have written. When you write it till here, then let me know. The question part, you can write it all together. Now you'll have the formula with you. So then I can discuss. Just let me know once written it till here. Okay. Okay, Muniba is done. Jesleen, let me know once you are done.
Done, ma'am.
Okay, now just turn your pages for the formula. So I'll not scroll up. Okay. First part we've already done. And what was our answer? 2000 ampere per meter square, per meter. Okay, per meter was our answer. Now, what was the second question? I hope the first part is clear. Is the first part clear? B naught is equal to mu naught H. So H will be B naught by mu naught. So that is 2000. Is that fine till here?
Yes, ma'am.
Okay. Coming to the net magnetic field. See, net magnetic field, basically, this is also known as the magnetic flux density. Okay. I'll just write whenever you have the term net magnetic field, this can be given as magnetic flux density. Okay. Now see, if you don't know the values of the magnetic field, let's say it's for a material. So you will have mu m into h. It's what we've studied, which we aren't aware of. This will it be? So Bm will be, mu m can be written as C. Relative permeability is mu naught divided by mu m. So from here, sorry, we have mu m, I have written it here. Your mu r is equal to mu m divided by mu naught. Okay, I just wrote it opposite. So from here you have the value of mu m as mu naught into mu r. Now see, both of these things are given in the question. Relative permeability is also given, and you already know the permeability of free space. So mu r into mu naught into h. So this is relative permeability is 400, mu naught is 4 pi into 10 to the power minus 7, and this is 2000. Okay, so this will be 16, and this is 32. So 32 pi into this is 2, this is 5. So 10 to the power minus 2 will be there. This much of Tesla. Okay, around 32 into pi will be what? Around 0.25 something you will get the answer. That was your magnetic field. Now, magnetic field in air, you know, magnetic field in the medium, you know. How to calculate the net magnetic field? Add both of it. It will be B naught plus Bm. So that was 8 pi into, what did we get here? 10 to the power minus 4. Okay. 8 pi into 10 to the power minus 4 plus this is 32 pi into 10 to the power minus 2. Later this can be solved, which is Tesla for the net magnetic field. Yes. Is the second part clear?
Yes, ma'am.
Yes, ma'am.
Okay. Sure. Are you sure? Do you want me to repeat? See, net magnetic field is B naught plus Bm. Bm is mu m into h. Mu m we don't know. That is mu r into mu naught into h. That's how we get the value of Bm. And mu naught already we calculated using B naught is equal to mu naught Ni for the solenoid because it was given as solenoid. Okay. Last part was I. There was a formula. Now check the notes which you have written. If I write the value of I, there was a formula which had this. H is equal to B by mu naught minus H. Was there a formula? B naught minus I like this. So from here, if I want I, can't I write I as B by mu naught minus H? Okay. So this B by mu naught, B means the net magnetic field. So C class, this you have to solve and check. Whatever is the value of the net magnetic field, 8 pi into 10 to the power minus 4 plus 32 pi into 10 to the power minus 2. divided by 4 pi into 10 to the power minus 7. This pi will be cancelled. This much minus 2000 will be the answer. Okay, so whatever answer you get, let me know. This much of ampere per meter will be the answer. Okay,
Yes, ma'am.
got it? Write down the question then, and if there's any doubt, please ask. And we'll just discuss the materials, and that will complete the chapter. Class, is it done? Completed? Jasleen, Muniba, you're present or you're sleeping? At least respond with a yes or a no.
Now I was calculating.
Okay, calculations you can do later. Calculations part, at least you have written it till here.
Yes, ma'am.
Okay. See, calculations you can do later. You will be able to get the answer. And answer is around, I think this will come almost equal to 1 by, this part will come almost equal to 1 test or something. Okay. See, there's a relation, there's a very important relationship between the susceptibility and the relative permeability. Okay. When we talk about the diamagnetic substances, they have weak magnetization. Okay, magnetic field is very weak. They have very weak magnetization in them. I'll share these things with you. So value of susceptibility is small here, and it is less than 0 means it is negative. And here the intensity of magnetization and magnetic intensity, they have the opposite signs. So mu r is 1 plus susceptibility, that is slightly less than 1. Let me explain you it in the tabular form. Then it will be clear, more clear here instead of this writing part. So the magnetization field, intensity magnetization, all these things we have already done. Yes, this part. Now what I'll do, I'll share a table also with all of you. So that from that table, it will be very easy to remember and learn. Okay, here everything is added. Let me just discuss this with you. And this will complete, this is the last part of the chapter, and this you have to remember by yourself. So I'll share a table, a little better table than this. So what are diamagnetic substances? As I told you that the electrons are left. Feeble magnetization means, I hope the text is clear, or is it very small? Are you able to see the text?
Yes, ma'am.
Okay. Feeble magnetization means very weak magnetization. Okay, diamagnetic substances have very weak magnetization in them. Paramagnetic, they also have weak magnetization. Only ferromagnetic substances have very strong magnetization. That's why I said temporary magnetization can be found in iron ball. Then the magnetic field will always be in the opposite direction to diamagnetic substance. It will be in the same direction for paramagnetic and ferromagnetic substances. Okay, and they are weakly repelled by the magnet. Weakly repelled by the magnets means the magnetization is itself very less, very it's not very strong. They are weakly repelled by magnets. They are weakly attracted by magnets. While ferromagnetics, they are strongly attracted. So weakly repelled, weakly attracted and strongly attracted. This is the difference. Now, this line means, or in fact, I'll just remove this. That means the tendency, they have diamagnetic substances have the tendency to move from a very stronger region of the magnetic field to a less strong region, means to a weaker region. Okay, while the paramagnetic substances have the tendency to move from weaker to the stronger parts, and same is with the ferromagnetic, weaker to stronger parts, while the diamagnetic, stronger parts of magnetic field to weaker parts. Then you have very few examples, basic exam. Just remember 3 examples from each, so that if the example part comes, you are able to write it. Copper, lead, that's it. Just remember the silver, till silver only remember. Sodium chloride, copper chloride, aluminium, chromium, these are examples of paramagnetic. For ferro, you should remember the alloy, alnico alloy, okay? And iron is there, you have cobalt, you have nickel, all these. Now, talking about the susceptibility, it's very small, very small. The value is very small for both dia and para. But what's the difference? Here it is negative and very less than 1. Here it is small, but it is positive. Okay. What about the ferromagnetic substances? They have the susceptibility big, greater than 1. And what about the relative permeability? Formula is 1 plus susceptibility. Relative permeability is 1 plus susceptibility. So relative permeability is slightly less than 1 for diamagnetic substance, greater or less than 1, okay, or you can say just greater than 1, slightly greater than 1 for paramagnetic, and very much greater than for diamagnetic. So this part you have to remember it by yourself, okay. Please just copy this quickly, this table, and I am sharing one table with both of you right now. Just if you receive, let me know. Meanwhile, you please write it. And just update me in the chat box when you are done. Muniba always does this, so Jessin, you also let me know so that I can scroll. Okay, while I'll share a table with you. Wait. All this has been written very properly in a table, so that I have scanned and share it on WhatsApp. So you will also probably receive it today only, and let me know if once you receive in the next class. Okay. So the same thing is written, but you'll not be able, just first see this and then go towards that. You'll be able to understand. Okay. And if you receive it on WhatsApp, please just update me as well. So all these things you have to learn it by yourself, Muniba and Jesleen. Okay, the questions come from this, and you just have to mug it up. You have to rote learn it. All these things, they are completely theoretical. No numerical is there in all this. You have to remember it. Okay, I'll share an assignment also with you. Your time is up. Do one thing. Take the screenshot of it. Okay, because you'll not be able to write much. And already I've shared the table, so most of the things are covered in the table. You don't have to actually refer to this. Just take the screenshot. Let me know once took. I'll scroll it because your time is up. So you can leave then.